Neptune is still inside our solar system. It orbits the same sun you see every morning. It follows the same gravitational rules as every planet you have ever learnt about in school. And yet, the first human beings to reach it would experience something no explorer in history has ever faced. They would watch Earth shrink, not just into a dot, but into a concept. Their messages home would take 4 hours to arrive and 4 hours to return. Sunlight at their destination would be 900 times dimmer than a sunny afternoon on Earth. And if anything went wrong, if a system failed, if a body broke, no rescue could reach them within a human lifetime. Neptune is not the edge of the solar system. It is the edge of human belonging. If you enjoy journeys that challenge how you see your place in the universe, a like and a subscribe go a long way toward helping us keep making them. Now, get yourself comfortable. Let's begin. You have seen the diagram 1,000 times. 8 planets lined up in a neat row stretching outward from the Sun. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Each one separated from the next by what looks like a polite gap, a comfortable spacing that suggests the solar system is a well-organized neighborhood where every planet has a reasonable address on the same street. You have seen this image on classroom walls. You have seen it in textbooks, on posters, in documentaries, on websites. You probably have some version of it lodged permanently in your memory, a mental model of home that makes the solar system feel knowable, bounded, manageable. A place where 8 worlds orbit one star in a tidy arrangement that a child can memorize before lunch. That diagram is a lie. Not a small lie. Not a rounding error or a simplification. A fundamental distortion of physical reality that warps how every human being on Earth thinks about the distances between the planets. The diagram compresses a distance ratio of nearly 60-1, Mercury to Neptune versus Earth to Mars, into what looks like equal spacing. It takes a solar system where the gap between Earth and Mars is a trivial suburban drive compared to the howling emptiness between Uranus and Neptune, and it flattens them into the same visual step. It makes Neptune look like it sits just a little past Saturn, maybe an afternoon farther along the same road. It makes the outer solar system look like an extension of the inner one, as if you could visit Jupiter, swing past Saturn, and cruise on to Neptune with a bit of extra fuel and a bit more patience. You cannot. And the reason you cannot is the reason this story exists. Neptune is not another planet in the same sense that Mars is another planet. It is not the next stop on a journey that begins at Earth and moves outward in manageable increments. It occupies a position in the solar system so remote, so profoundly separated from the warm inner worlds where human spaceflight has operated, that reaching it would require crossing a threshold that changes the meaning of every word we use to describe exploration. Distance, communication, rescue, return, home. Every one of those words works fine when you are talking about the Moon, or Mars, or even Jupiter. At Neptune, every one of them breaks. But to understand why, you first have to understand what Neptune actually is and where it actually sits, not on the classroom poster. In reality, Neptune is the 8th and outermost major planet in the solar system. It is an ice giant, a category it shares only with its nearest neighbour, Uranus. Unlike the gas giants Jupiter and Saturn, which are composed primarily of hydrogen and helium, Neptune and Uranus contain substantial amounts of heavier volatile compounds, water, ammonia, and methane compressed into exotic states by crushing pressures deep within their interiors. Neptune's mass is roughly 17 times that of Earth. Its equatorial diameter spans nearly 31,000 miles, almost 4 times wider than our planet. If Neptune were hollow, you could fit nearly 60 Earths inside it. Neptune's atmosphere is a violent, frigid hell. Despite receiving only a fraction of the sunlight that drives weather on Earth or even Jupiter, Neptune hosts the fastest winds ever measured on any planet in the solar system. Sustained wind speeds reach up to 1,200 miles per hour, with gusts measured at nearly 1,500. These winds blow mostly westward, opposite to the planet's rotation, and drive enormous storm systems that can rival Earth in size. When Voyager 2 flew past in 1989, it discovered a massive anticyclonic storm dubbed the Great Dark Spot, an Earth-sized vortex spinning in Neptune's southern hemisphere. 5 years later, when the Hubble Space Telescope turned its gaze toward Neptune, the Great Dark Spot had vanished entirely. Neptune's atmosphere is so dynamic, so energetically violent, that planet-sized storms appear and dissolve within years. No one fully understands where all that energy comes from. Neptune radiates roughly 2.6 times more heat than it receives from the Sun, suggesting a powerful internal heat source whose mechanism remains an open scientific question. Neptune's largest moon, Triton, is almost certainly a captured object from the Kuiper Belt, the vast ring of icy bodies that extends beyond Neptune's orbit. Triton orbits Neptune in the wrong direction, retrograde, opposite to the planet's rotation, a gravitational signature of capture rather than co-formation. Its surface is colder than any planet in the solar system, a frozen shell of nitrogen and methane ice that should be geologically dead. And yet, Voyager 2 found geysers on Triton. Active plumes of nitrogen gas erupt from beneath the surface, spraying dark material miles into the moon's tenuous atmosphere. Triton is geologically alive despite orbiting a planet so far from the Sun that the concept of warmth barely applies. All of this makes Neptune an extraordinary scientific target, but none of it explains why reaching Neptune with human beings would constitute something fundamentally different from any mission humanity has ever contemplated. To understand that, you have to grapple with the distance. Neptune orbits the Sun at an average distance of approximately 30 astronomical units. 1 astronomical unit is the average distance from the Earth to the Sun, roughly 93 million miles or 150 million kilometers. Multiply that by 30. Neptune sits approximately 2.8 billion miles from the Sun. Written in kilometers, that figure is 4.5 billion. These are numbers that the human brain can process as digits on a page, but cannot translate into anything resembling intuitive understanding. 2.8 billion miles has no emotional weight. It is too large to feel. So let us try to make it feel like something. And not with numbers, with objects you can hold. Imagine building a scale model of the solar system using a basketball as the Sun. A standard basketball is about 9.5 inches in diameter. At this scale, the Sun has been shrunk by a factor of roughly 9.2 billion. Apply that same factor to everything else, and you get a solar system you can walk through, almost. Earth, at this scale, becomes a tiny bead, roughly 2 millimeters across, smaller than a peppercorn, smaller than the head of a pin. It sits approximately 86 feet from the basketball. You could stand at Earth and still see the Sun clearly across the length of a large room. Mars would be a slightly smaller grain, about 1.4 millimeters, sitting 130 feet away, still in the same parking lot, still within shouting distance. Jupiter, a marble about 1 inch across, would sit roughly 450 feet from the basketball a few blocks away. You are starting to need a real walk, but you could still do it comfortably before your coffee gets cold. Saturn, a slightly smaller marble, would be about 830 feet out. You are now a serious walk from the Sun, but the distances still feel navigable. You could turn around and jog back in a few minutes. The inner solar system, everything from Mercury to Saturn, fits within a space that a human being can traverse on foot in roughly 15 to 20 minutes. Now find Uranus. At this scale, Uranus is a small bead sitting approximately 1/3 of a mile from the basketball. You have left the building. You have left the parking lot. You are standing several blocks from the Sun, holding a sphere the size of a small marble, and you are not even at the last planet yet. Neptune sits approximately 1/2 a mile from the basketball. To visit Neptune in your scale model, you need to walk for 1/2 a mile down the street, carrying a bead roughly 9 millimeters wide. Neptune, 4 times the diameter of Earth, has been reduced to a small pea, and when you arrive, you turn around and look back toward the basketball. You cannot see it. It is 1/2 a mile away, an object 9.5 inches across, lost behind buildings and trees and distance. The Sun, in your scale model, is invisible from Neptune, and Neptune, from the Sun, is a pea lost in a neighbourhood. This is the solar system at a scale you can touch, and the lesson it teaches is brutal. The inner planets live in the Sun's front yard. Jupiter and Saturn live on the same block. Uranus and Neptune live in a different part of town entirely, separated from the rest by a gap that dwarfs everything that came before. The solar system is not a row of evenly spaced objects. It is a tight cluster near the centre, and a scattering of lonely worlds in the outer darkness, separated by distances that make the inner system look like a single room. And in this model, a human spacecraft, the fastest crewed vehicle ever built, the Apollo Command Module returning from the Moon at roughly 25,000 miles per hour, would be moving at roughly a quarter of an inch per hour. It would take over 10,000 years to crawl from the basketball to the pea. The fastest thing humans have ever ridden would be functionally invisible at the scale of the solar system itself. If you could drive a car to Neptune at highway speed, 70 miles per hour, without stopping for fuel, food, sleep, or death, the drive would take approximately 4,500 years. You would have started driving around the time the ancient Egyptians were building the Great Pyramid at Giza. You would still not have arrived. If you could fly a commercial airliner to Neptune at 550 miles per hour, the flight would take roughly 580 years. You would have boarded the plane nearly half a century before Columbus reached the Americas. You would be landing only now. Light itself, the fastest phenomenon in the known universe, travelling at 186,000 miles per second, requires over 4 hours to travel from the Sun to Neptune. When sunlight leaves the solar surface and races outward at the absolute speed limit of physics, it reaches Earth in about 8 minutes. It reaches Mars in roughly 12.5 minutes. It reaches Jupiter in about 43 minutes. It reaches Saturn in approximately 79 minutes. To reach Neptune, that same light must travel for 4 hours and 10 minutes. More than half a standard workday passes while a photon moving faster than anything else in the universe can move crosses the void between the Sun and the 8th planet. This light travel time is not merely an astronomical curiosity. It is the foundation of every problem a human crew would face at Neptune, because light travel time is also communication time. Radio signals, the technology that connects every spacecraft to Earth, travel at exactly the speed of light. A message sent from Earth to a spacecraft at Neptune takes over 4 hours to arrive. A reply takes over 4 hours to return. A single exchange, one question, one answer, consumes more than 8 hours. That is not a conversation. That is not even close to a conversation. On the International Space Station, astronauts can video call their families with less than a second of delay. On the Moon, Apollo astronauts experienced a one-way delay of roughly 1.3 seconds, a round trip of about 2.5 seconds. At Neptune, the one-way delay alone is roughly 11,000 times longer than what the Apollo crews experienced. The implications of that number will become clear shortly, but for now, understand this. Neptune is so far away that the speed of light itself becomes a prison wall between a crew and everything they have ever known. But the distance to Neptune does not simply make existing problems worse. It reveals something about the structure of the solar system that the classroom diagram conceals entirely. The solar system is not a smooth, evenly spaced arrangement. It is violently lopsided. The inner planets Mercury, Venus, Earth, Mars are bunched together within roughly 1.5 astronomical units of each other. This is the warm, rocky, sun-drenched neighbourhood where all of human experience has taken place. Mars, the farthest destination that any serious crewed mission has ever targeted, sits at about 1.5 AU from the Sun. On the classroom diagram, Mars looks like it is reasonably close to Earth, and in solar system terms it genuinely is. Then comes the asteroid belt, and then comes Jupiter at 5.2 AU. Already, you have more than tripled the distance from Earth to Mars. Saturn at roughly 9.5 AU, Uranus at roughly 19 AU, and then, after another 11 AU of emptiness, a gap wider than the entire distance from the Sun to Saturn, comes Neptune, at 30 AU. That structural fact deserves a moment of attention, because it is easy to gloss over and critical to understand. The gap between Uranus and Neptune alone, approximately 11 AU, is larger than the distance from the Sun to Saturn. The outermost stretch of the planetary solar system contains more empty space than the entire inner and middle solar system combined. Neptune does not sit at the far end of a continuum. It sits across a chasm. This chasm is not merely a problem of patience. It is a problem of physics, engineering, biology, and psychology all at once. Every challenge that a spacecraft must overcome — fuel, food, radiation shielding, equipment maintenance, communication, crew health scales with distance and time, and at Neptune, both distance and time reach values that push beyond the limits of any technology humans currently possess or are seriously developing. Consider what it took for the only spacecraft ever to visit Neptune to get there. Voyager 2 launched from Cape Canaveral on August 20th, 1977. It did not fly directly to Neptune. It could not. A direct flight from Earth to Neptune using conventional chemical propulsion would have taken approximately 30 years. Instead, it's the same rare planetary geometry that Voyager exploited. This alignment allowed the spacecraft to perform gravity, assists at Jupiter, Saturn, and Uranus, using each planet's gravitational field to accelerate and redirect its trajectory. Each flyby bent the spacecraft's path and added velocity without burning a single gram of additional fuel. It was a masterpiece of celestial mechanics, a cosmic billiard shot that took advantage of planetary positions that would not repeat until the 22nd century. Even with those gravity assists, the journey took 12 years. Voyager 2 arrived at Neptune on August 25, 1989, travelling at an average velocity of roughly 19 kilometers per second, about 42,000 miles per hour. It flew past Neptune's North Pole at a distance of approximately 3,000 miles, captured the first and still the only close-range images of the planet and its moons, and then continued outward on a trajectory that would eventually carry it into interstellar space. The encounter lasted months if you count the approach and departure phases, but the close flyby itself was measured in hours. 12 years of travel for a few hours of proximity to the most distant planet. What Voyager 2 encountered at Neptune revealed just how alien the outer solar system truly is, not only in terms of planetary science, but in terms of basic sensory experience. That extreme faintness of illumination created an unprecedented technical challenge for the Voyager imaging team. At Jupiter, the spacecraft had abundant light to work with. Photographs were relatively straightforward. At Saturn, the light was dimmer but still manageable. At Uranus, the reduced illumination began to cause difficulties, and the images had a hazy, washed-out quality that frustrated scientists. At Neptune, the problem became severe. The planet was so dimly lit that Voyager 2's cameras needed long exposure times to capture usable images, but the spacecraft was hurtling past Neptune at tens of thousands of miles per hour, meaning that any exposure long enough to gather sufficient light would also smear the image into an unusable blur. Engineers solved this problem by programming the spacecraft to rotate during each exposure, counteracting its own motion to hold the camera steady against the dim target, a technique essentially equivalent to panning a camera to track a moving subject, except performed autonomously by a robot 2.8 billion miles from the nearest human hand. The solution worked. Voyager 2 returned stunning images of Neptune's cloud bands, storm systems, and ring arcs. But the difficulty of photographing Neptune, the sheer technical ingenuity required to see a world so dimly lit, underscored a truth that the images themselves could not fully convey. Neptune exists in a regime of faintness that human senses were never designed for. The light at Neptune is not merely dim, it is the light of a world that sits at the outermost edge of the sun's ability to illuminate anything at all. A crew arriving at Neptune would not experience darkness. The sun, though reduced to a point, would still be the brightest object in the sky by a wide margin, but they would experience a quality of light that no human being has ever lived under. A permanent twilight, a world where noon looks like the last grey minutes before nightfall on Earth. A sky in which the concept of daytime has lost most of its meaning. And Voyager 2 is a robot, a machine that does not need food, water, air, sleep, companionship, or psychological support. A machine that does not age in any biological sense, that does not suffer from radiation-induced cancer, that does not experience loneliness or despair. A machine that weighs roughly 825 kilograms, less than a small car. The engineering challenge of sending Voyager 2 to Neptune was immense. The engineering challenge of sending human beings to Neptune is of a categorically different order. No crewed spacecraft design exists or is under serious development that could sustain human life for 12 years of deep space transit. The longest continuous human spaceflight on record is Valery Polyakov's 437 days aboard the Russian space station Mir, completed in 1995. That is roughly 1 year and 2 months, aboard a station in low Earth orbit that received regular resupply missions, maintained real-time communication with the ground, and orbited within the protective envelope of Earth's magnetosphere. A Neptune transit would require sustaining human life for roughly 10 times that duration, in a spacecraft far smaller than Mir, with no resupply, no real-time communication, no magnetospheric shielding, and no possibility of emergency return. The propulsion problem alone is staggering. Voyager 2 reached Neptune only because it did not need to slow down. It flew past the planet at tremendous speed, captured data during the flyby, and continued onward. A crewed mission cannot do this. A human crew needs to arrive at Neptune and enter orbit, which requires decelerating from interplanetary cruise speed, a maneuver that demands enormous amounts of fuel. And if the mission includes a return to Earth, the fuel requirements roughly double again. The total velocity change, the delta V for a Neptune round trip, exceeds the capability of any propulsion system that currently exists or is under funded development. Even the most ambitious robotic mission concepts for Neptune reflect how daunting the distance is. Neptune Odyssey, a flagship-class orbiter mission studied by a team led by the Johns Hopkins Applied Physics Laboratory, proposes a launch in the early 2030s aboard a heavy-lift rocket. Using a direct trajectory to Neptune without a Jupiter gravity assist, the cruise phase would last 16 years. With a Jupiter gravity assist, it could be shortened to approximately 12 years, but the Jupiter flyby window requires launching before 2032. The spacecraft would arrive at Neptune no earlier than the mid-2040s, more than 2 decades after mission planning began. And this is a robotic mission, a probe that weighs a fraction of what a crewed vessel would require. As of 2026, no space agency on Earth has approved a mission to Neptune of any kind. Not robotic, not crewed. The Planetary Science Decadal Survey, the document that sets priorities for NASA's planetary exploration program, recommended a Uranus orbiter as the next ice giant mission, prioritized over Neptune largely for logistical and cost reasons. Uranus is closer. Uranus is easier to reach. Uranus has more favorable launch windows in the near term. Neptune, the report implicitly acknowledged, is a harder problem, even for robots. For humans, it may not be a solvable problem at all, not with existing technology, not with technology under development, and possibly not with any technology that the current generation of engineers will live to see built. And yet, Neptune is still inside the solar system. It orbits the same star. It follows the same gravitational laws. It is not some exotic destination in another galaxy, not a planet circling a distant sun, not a world that requires faster-than-light travel or wormholes or science fiction. It is right here, in our own system, separated from us by nothing but vacuum and distance. 30 astronomical units of ordinary, unremarkable, empty space. That is what makes Neptune so unsettling as a human destination. It is not alien. It is not impossible to understand. It is not beyond the reach of physics. It is simply far, farther than human intuition can process, farther than human technology can comfortably bridge, farther than the emotional architecture of human connection can stretch without snapping. Neptune sits at a distance where every assumption we carry about what it means to be an explorer that you can call home, that someone can come get you, that Earth is still part of your daily reality begins to dissolve. The classroom diagram hides this. It makes Neptune look like it is just past Saturn, just another step on the same road. It compresses billions of miles of emptiness into a few centimeters of whiteboard space and makes the entire solar system look like a garden you could walk across in an afternoon. But the solar system is not a garden, it is a desert. And Neptune sits so deep in that desert that reaching it would mean crossing into a region where the word home starts to lose its meaning. The ancient Greeks looked up at the night sky and saw 5 wandering stars: Mercury, Venus, Mars, Jupiter, Saturn, moving against the fixed background of constellations. They had no idea that 2 more planets existed beyond Saturn's orbit, hidden in the darkness, too faint for any unaided human eye to detect. Uranus was not discovered until 1781, when William Herschel spotted it through a telescope and initially mistook it for a comet. Neptune was not found until 1846, and it was not found by looking, it was found by calculating. French mathematician Urbain Le Verrier noticed that Uranus was not moving exactly as Newton's laws predicted. Something was pulling on it, distorting its orbit, tugging it away from where the math said it should be. Le Verrier calculated the position and mass of an unseen planet that could account for the discrepancy. He sent his prediction to the Berlin Observatory. On September 23, 1846, astronomer Johann Galli pointed a telescope at the coordinates Le Verrier had provided and found Neptune within 1 degree of the predicted position. It was the first planet discovered through mathematics rather than observation. The first world located by the power of equations rather than the power of human eyes. There is something fitting about that. Neptune has always been a planet that resists human senses. You cannot see it without a telescope. You cannot feel its gravitational influence from Earth. You cannot detect its light, its heat, its presence through any channel that human biology provides. It exists at a distance where the sun itself, the object that dominates the sky and sustains all life on Earth, has diminished to a point of light roughly 900 times dimmer than what you experience on a sunny afternoon. NASA has described noon on Neptune as resembling dim twilight. Not darkness, not quite, but a pale, ghostly illumination that would feel nothing like the warmth and brilliance of terrestrial daylight. A crew arriving at Neptune would look back toward the sun, and they would see it as a sharp point of light, brilliant but no longer warm, not a disk, not a source of warmth, a point, and somewhere near that point, invisible, lost in the glare, would be Earth. The solar system that humans think they understand, the tidy neighbourhood of 8 planets orbiting a friendly star, is a fiction of scale. The real solar system is a vast, cold, mostly empty structure where matter clusters near the centre and thins to almost nothing at the edges. The inner planets are islands of rock and warmth huddled close to the sun. The gas giants are cold, massive sentinels standing at the boundary between the relatively compact inner system and the sprawling emptiness beyond. And Neptune stands at the outer wall of that boundary, the last major planet, the final gravitational anchor before the solar system dissolves into the scattered ice of the Kuiper Belt and eventually into the interstellar void. Getting a robot to Neptune is a generational engineering challenge. Getting a human being to Neptune is something else entirely. It is a challenge that forces us to confront not only the limits of our technology, but the limits of our biology, our psychology, and our deepest assumptions about what it means to leave home and still be connected to it. But distance is just a number. The real question is what that number does to everything humans depend on: communication, rescue, sunlight, and the feeling that someone back home is still listening. And the answer to that question is where this story truly begins. Every astronaut who has ever lived in space has relied on one invisible lifeline more than any other. Not oxygen, though oxygen is critical. Not water, though water is essential. The lifeline that holds human beings together across the void is communication. The ability to hear a familiar voice. The ability to ask a question and receive an answer. The ability to say something is wrong, and here is what to do. Every crewed mission in the history of spaceflight, from Yuri Gagarin's single orbit in 1961 to the continuous occupation of the International Space Station has operated within a communication environment where Earth was, for all practical purposes, right there, present, immediate, reachable. At Neptune, that lifeline does not weaken, it does not fray, it shatters completely. To understand why, you first need to appreciate how much human spaceflight depends on real-time contact with the ground. On the International Space Station, astronauts are never truly alone. They maintain near-continuous communication with mission control centers in Houston, Moscow, and other facilities around the world. The delay is negligible, a fraction of a second, indistinguishable from a normal phone call. When an equipment malfunction occurs, ground controllers can see the same telemetry the crew sees, diagnose the problem in real time, and talk the astronaut through the repair step by step. When a medical emergency arises, flight surgeons on the ground can observe the patient through video, ask questions, receive answers instantly, and guide treatment as it happens. When a crew member is struggling psychologically, experiencing anxiety, insomnia, interpersonal conflict, or the slow erosion of morale that comes with months of confinement, they can schedule a private video call with a psychologist who responds to their words as they speak them. This support infrastructure is not a luxury. It is the reason human spaceflight works. NASA has studied this dependency extensively. The agency understands that astronauts are not self-sufficient units. They are human beings, embedded in a web of real-time support that stretches from the spacecraft all the way down to offices and laboratories on the ground. Remove that web, and you remove the system that keeps people functional, safe, and sane in the most hostile environment our species has ever inhabited. Now consider what happens when you introduce a communication delay. NASA is already deeply concerned about the delays that a crewed Mars mission would impose. Mars sits at a variable distance from Earth, ranging from about 3 light minutes at its closest to roughly 22 light minutes at its farthest. A round-trip exchange, one message sent, one reply received, could take anywhere from 6 minutes to 44 minutes, depending on orbital positions. This is not a hypothetical concern. It is one of the central challenges identified in NASA's Human Research Program, and it has been studied in analog environments designed to simulate the isolation and confinement of deep space missions. At NASA's Johnson Space Center, researchers operate the Human Exploration Research Analog, known as HERA, a sealed habitat where volunteer crews live in isolation for weeks or months at a time, performing tasks and interacting with a simulated mission control under controlled communication delays. The findings from these studies are sobering. Even modest delays as short as 50 seconds each way produce measurable degradation in crew performance and well-being. In a study conducted aboard the International Space Station itself, researchers imposed a 50-second one-way communication delay during certain tasks and measured the impact. The results showed that crew well-being and the perceived quality of communication dropped significantly during delayed interactions compared to real-time controls. Stress and frustration increased. Task efficiency declined. The rapport between crew members and mission support personnel weakened. 50 seconds, less than a minute of delay, and the human system that holds spaceflight together already starts to crack. At 5 minutes of delay, real-time problem-solving becomes functionally impossible. You cannot walk someone through a repair procedure when every instruction takes 10 minutes to deliver and confirm. You cannot coach someone through a medical intervention when the patient's condition may change 3 times before your guidance arrives. You cannot provide emotional support when the person you are trying to help has already moved through the crisis, or deepened into it by the time your words reach them. 5 minutes of delay transforms communication from a conversation into a series of disconnected monologues. On Mars, at maximum distance, the delay is 22 minutes each way, 44 minutes for a round trip. NASA considers this a serious and partially unsolved challenge. Research papers describe it as a fundamental threat to crew autonomy, team cohesion, and mission safety. The agency is actively developing countermeasures, artificial intelligence systems, automated psychotherapy tools, enhanced crew training protocols designed to help astronauts cope with the loss of real-time ground support during a Mars mission. The underlying message is clear. Even at Mars distances, The communication delay is dangerous enough to require years of research and technological innovation to manage. Now multiply that delay by a factor of 10. Neptune's average distance from the Sun is 30 astronomical units. Earth's distance from Neptune varies with orbital positions, but the one-way light travel time is approximately 4 hours. Not 4 minutes, 4 hours. A single message sent from a spacecraft at Neptune takes 4 hours to reach Earth. The reply takes 4 hours to return. A round-trip exchange consumes 8 hours. That is a full working day on Earth. A crew member at Neptune could report a fire at breakfast, and the earliest possible response from mission control would arrive around dinner time. Sit with that number. Let it become concrete. Imagine an astronaut at Neptune discovers a crack in a pressure seal on the crew habitat. Air is leaking. The crew has hours, maybe less, before the leak becomes critical. On the International Space Station, this scenario triggers an immediate, coordinated response. The crew reports the problem. Ground controllers pull up structural diagrams. Engineers identify the likely location. Flight directors talk the crew through isolation procedures, sealing hatches, rerouting airflow, applying temporary patches. The whole process unfolds in real time, with dozens of experts contributing simultaneously. At Neptune, the crew reports the leak. Then they wait. For 4 hours, they hear nothing. No guidance, no reassurance, no expert voice walking them through the procedure. They are alone with the hissing of escaping air and whatever training they can recall and whatever tools they can find. 4 hours later, Mission Control receives the message. Engineers scramble to analyze the problem. They formulate a response. They transmit it. 4 hours after that, the crew receives the instructions. But 8 hours have passed since the leak was first detected. If the leak was severe, the crew may already be dead. If it was moderate, they have either solved the problem themselves or they have not. In either case, the instructions from Earth arrive as history, not help. They arrive after the crisis has ended, one way or another. This is not an edge case. This is the fundamental reality of every emergency at Neptune distance. Medical emergencies, equipment failures, structural damage, software malfunctions, psychological breakdowns. Every crisis that could threaten a crew at Neptune must be resolved entirely by the crew, with no real-time input from Earth. The nearest expert, the nearest doctor, the nearest psychologist, the nearest engineer is 4 hours of light-speed travel away. In terms of practical response time, Earth might as well be in another star system. Consider the medical implications. On the International Space Station, if an astronaut suffers a serious injury or a medical emergency, a cardiac event, a severe allergic reaction, an accidental trauma, the crew can consult with flight surgeons in real time. The surgeon can observe the patient through live video, ask diagnostic questions, receive immediate answers, and adjust treatment recommendations as the situation evolves. In the most extreme scenarios, the crew can evacuate to Earth within hours using a Soyuz or Crew Dragon capsule. The station is never more than a few hundred miles above the planet's surface. At Neptune, there is no evacuation. There is no hospital within a decade of travel. A crew member who develops appendicitis, or suffers a stroke, or breaks a femur, must be treated by crewmates who are scientists and pilots, not surgeons, using whatever medical equipment was packed into the spacecraft before launch. They cannot consult with a doctor in real time. They can send a description of the symptoms and wait 8 hours for a response. If the condition is immediately life-threatening, 8 hours is an eternity. The patient may survive or die based entirely on the crew's ability to improvise, not on the quality of medical advice available on Earth. And medicine is only one domain where the delay becomes lethal. Psychological support, which NASA has identified as one of the most critical factors in long-duration spaceflight, collapses entirely at Neptune distance. The psychological research is unambiguous. Prolonged isolation and confinement degrade human mental health. Anxiety, depression, irritability, insomnia, interpersonal conflict, cognitive decline. All of these have been documented in astronauts, submariners, Antarctic winter-over crews, and participants in spaceflight analog studies. NASA's Human Behavior and Performance Program has spent decades developing countermeasures. Private psychological conferences, family video calls, crew care packages, lighting systems that simulate natural circadian rhythms, recreational activities designed to break monotony. All of these countermeasures depend, directly or indirectly, on the crew's connection to Earth. The private psychological conference works because the astronaut can talk to a therapist who listens and responds in real time. The family video call works because the astronaut can see their child's face and hear their voice without meaningful delay. The care package works because it arrives within weeks, a tangible reminder that people on Earth are thinking about the crew. At Neptune, none of these systems function. A private psychological conference becomes an exchange of recorded video messages, each sent into the void and returned hours later. The therapist cannot respond to the astronaut's emotional state in the moment. They can only respond to the state the astronaut was in 4 hours ago, which may bear no resemblance to the state they are in now. A family video call becomes a delayed correspondence where the child on the screen has already gone to bed by the time the parent's reply arrives. The emotional immediacy that makes these connections, sustaining the feeling that someone is right there, listening, caring, responding, is annihilated by the delay. Research conducted in NASA's analog environments has shown that perceived social support declines measurably over time in isolation, even when communication with the outside world is available. Crew members in Hera campaigns who experience communication delays reported feeling less connected to mission control, less supported by external sources, and more reliant on fellow crew members for emotional sustenance. These findings emerge from missions lasting 45 days, with delays of only a few minutes. Extrapolate those results to a mission lasting years, with delays of 4 hours, and the psychological picture becomes deeply alarming. The crew would not merely feel isolated. Instead, the crew enters a degree of separation from human civilization that has no precedent in the history of our species. NASA researchers have begun to acknowledge that deep space missions will require astronauts to function with unprecedented levels of autonomy, not merely in operational tasks, but in psychological self-management. Automated psychotherapy systems, AI companions, and preloaded mental health resources are all under investigation as potential countermeasures for missions where real-time Earth-based support is unavailable. The underlying assumption in this research is revealing. By the time humans venture beyond Mars distances, the connection to Earth that has sustained every previous space mission will have degraded to the point where it can no longer serve its intended function. The crew will be on their own. At Neptune, they would be more on their own than the phrase conveys. And then there is the dimension of this isolation that no amount of technology can address: the visual disappearance of home. At 30 AU, the inverse square law has reduced sunlight to a ghost of what Earth receives. Double the distance and you receive 1/4 the light. Triple it, 1/9. At 30 times the distance, the sun delivers barely 0.1% of the illumination that falls on Earth. What would noon look like under that light? Not darkness, but something closer to the last grey moments before nightfall. Not darkness, but a pale, attenuated glow that would feel nothing like the warm, bright daylight that humans evolved under and depend on for circadian regulation, vitamin D synthesis, and basic psychological well-being. The sun, from Neptune, is not the blazing disk that dominates Earth's sky. It is a very bright point of light, still the brightest object in the sky by far, still recognizably the sun, but no longer a disk, no longer warm, no longer the source of daylight as any human being has ever experienced it. And Earth, from Neptune's distance, cannot be seen without a telescope. This is not a metaphor, it is optics. Earth is a small, rocky planet reflecting sunlight. At a distance of approximately 29 astronomical units, the minimum separation between Earth and Neptune, our planet's apparent brightness would be far too faint to detect without optical instruments. A crew at Neptune could point a telescope back toward the inner solar system and find Earth as a pale blue pixel. But step away from the eyepiece, look out the window, and there is nothing. No blue dot, No visible reminder that the world they came from still exists. Just stars, and darkness, and the cold blue sphere of an ice giant turning beneath them. Every previous human explorer in history has had the option of looking up and seeing something that connected them to home. Sailors on the open ocean could see the same sun and the same stars that shone over their port of departure. Antarctic researchers could watch the same moon that rose over their families' houses. Apollo astronauts could look out their windows and see Earth enormous, luminous, heartbreakingly beautiful hanging in the black sky, close enough that its continents were visible, close enough that they could point to the city where their children slept. A crew at Neptune has none of this. Earth is gone from the sky, the sun has shrunk to a point. The constellations are essentially unchanged. The stars are so distant that Neptune's orbital position shifts them imperceptibly, but the emotional anchor, the visual proof that home exists and is nearby, has been removed. The crew would inhabit a sky that looks almost identical to the one they left, minus the one object that made it feel like theirs. This visual severing is not a minor psychological detail. NASA research has consistently emphasized the importance of Earth observation, looking down at the planet through spacecraft windows, as one of the most powerful countermeasures against the psychological toll of spaceflight. Astronauts on the International Space Station describe the experience of seeing Earth as profoundly restorative. The blue oceans, the swirling clouds, the green continents, the thin, bright line of the atmosphere, these visual inputs remind the crew, at a visceral level, that the world they belong to is right there, just below them, waiting for their return. Some astronauts have described photography of Earth as their most valued recreational activity, a practice that simultaneously combats monotony, reinforces connection to home, and generates the deep emotional response that psychologists call the overview effect. At Neptune, the overview effect does not exist. There is no Earth to photograph through the window. There is no home below. There is only a foreign planet, a captured moon with nitrogen geysers, and a sun that has been reduced to a star. And perhaps the most disorienting aspect of all is the temporal displacement that the communication delay creates. On the International Space Station, when an astronaut sends a message to family, the reply arrives almost instantly. The conversation exists in shared time. Both parties inhabit the same present moment. At Neptune, the crew exists in a different temporal reality than the people they left behind. A message sent from Neptune is a dispatch from the past by the time it reaches Earth. The reply is a dispatch from the past by the time it reaches Neptune. Nothing is simultaneous, nothing is current. Everything is delayed, outdated, stale. A crew member's child could be born, and the parent at Neptune would not learn of it for 4 hours. Their congratulatory reply would not arrive for another 4. The child would be 8 hours old before a single complete exchange had occurred. A crew member's parent could die, and the news would travel for 4 hours through the void before reaching the grieving child. Their tears, their words of remembrance, their need for comfort would radiate outward from Neptune at the speed of light, and arrive at a world where the funeral has already concluded, where the other mourners have already gone home, where the moment of shared grief has passed without them. This is not theoretical. These are the kinds of events that occur over the course of years and decades of human life. A Neptune mission lasting a minimum of 12 years one way, and possibly much longer, would encompass births, deaths, marriages, divorces, illnesses, recoveries, elections, wars, natural disasters, technological revolutions, and every other category of human event that constitutes the fabric of life on Earth. The crew would experience all of it on an 8-hour delay. They would learn about changes in the world they left behind only after those changes had already become history. They would respond to joys and sorrows that had already faded by the time their responses arrived. Over months and years of this temporal dislocation, Earth would undergo a transformation in the crew's psychological experience. It would stop being a place that exists in the present and become a place that exists only in the past. Every piece of information from Earth would arrive with a timestamp that says, "This happened 4 hours ago." Every reply from the crew would arrive on Earth with the same disclaimer. The two worlds, the one at Neptune and the one at Earth, would drift apart not just physically, but temporally, emotionally, experientially. The crew would still know that Earth exists. They could still receive news, updates, even entertainment transmitted across the void. But the Earth they receive would always be an old Earth, a delayed Earth, an Earth that has already moved on from the moment being described. This is what 4 hours of silence means. Not merely that communication is slow, not merely that emergencies cannot be addressed in real time. It means that the fundamental human experience of sharing the present with the people you love, of existing in the same moment, reacting to the same events, feeling the same feelings at the same time is taken away. The crew at Neptune would be marooned not only in space but in time. They would inhabit a perpetual present that Earth can never touch in the moment it is happening. And this only addresses the delay. It does not address the fragility of the communication link itself. Voyager 2, the only spacecraft ever to visit Neptune, communicated with Earth via the Deep Space Network, a system of enormous radio antennas in California, Spain, and Australia. By the time Voyager 2 reached Neptune, its radio signal was so weak that the Deep Space Network had to expand its antenna dishes from 64 meters to 70 meters in diameter and link multiple antennas together to hear the spacecraft at all. Data transmission rates at Neptune distance dropped to painfully low levels compared to what was possible at Jupiter or Saturn. A crewed mission would require far higher data rates to support voice communication, video, telemetry, and medical data, all of which would need to be transmitted across 2.8 billion miles of vacuum, using power systems that must function without interruption for over a decade. Any disruption, a solar conjunction that places the Sun between Earth and Neptune, an equipment failure on the spacecraft's communication array, a power fluctuation, a pointing error in the antenna alignment could sever the link entirely. The crew would not experience a degraded connection. They would experience silence, total, absolute silence. No signal going out, none coming in, for hours or days or longer, depending on the nature of the failure. And in that silence, they would confront the deepest fear that every human being carries in some form. The fear of being completely, irrevocably alone. Every human being who has ever left home to explore unknown territory has carried with them some version of a tether, a rope, a trail, a compass bearing, a radio frequency that connects them to the world they came from and offers the implicit promise that they can return, or at least be heard. At Neptune, the tether is 4 light hours long, fragile as a whisper, and vulnerable to disruptions that no one on Earth can fix. But communication is only part of the story. The deeper question is what happens when you realize that not only can no one hear you in real time, no one can reach you at all. There is a moment in every conversation about deep space exploration where the word farther stops being adequate. You can say that Neptune is farther than Mars. You can say it is farther than Jupiter, farther than Saturn, farther than Uranus. All of these statements are true, and all of them are misleading, because they imply that Neptune sits at the far end of a single spectrum, that it occupies the same scale as Mars, just with a bigger number attached, as if the difference between a Mars mission and a Neptune mission were the difference between a 5-hour flight and a 10-hour flight. Same airplane, same experience, just longer. That is not what Neptune represents. Neptune represents a boundary, not a line drawn on a map, not an official designation, but a physical threshold where the cumulative weight of distance, time, fuel, radiation, biological aging, mechanical degradation, and psychological endurance converges into something that no longer resembles exploration in any sense that human history has ever used the word. Mars is hard. Jupiter would be harder. Saturn, harder still. But these destinations sit along a continuum where the challenges, while escalating, remain recognizably similar in kind. More fuel, more time, more shielding, more supplies. You can imagine solving each problem with a larger version of the same solution. Neptune breaks the continuum. At Neptune, the challenges do not merely grow larger, they change category. And that categorical shift is what separates a mission that is extraordinarily difficult from a mission that may be functionally impossible for human beings. Start with the most fundamental variable: time. Under the most plausible near-future propulsion systems, chemical rockets augmented by gravity assists a crewed mission to Neptune would require somewhere between 12 and 20 years of one-way transit, depending on the trajectory, the launch window, and whether a Jupiter gravity assist is available. The lower end of that range, 12 years, assumes an optimal planetary alignment and a trajectory similar to the one Voyager 2 used. But Voyager 2 did not need to slow down. It flew past Neptune at interplanetary cruise speed, gathered data during a brief encounter window, and continued outward into interstellar space. A crewed mission cannot do this. A crewed mission needs to arrive at Neptune and stop to enter orbit, or at minimum to decelerate enough for a sustained encounter. That deceleration requires burning enormous amounts of fuel, which must be carried from Earth, which adds mass, which requires more fuel to accelerate from Earth in the first place, which adds more mass. The rocket equation is pitiless. Every kilogram of deceleration fuel demands additional kilograms of acceleration fuel, and the total mass spirals upward exponentially. This is why realistic estimates for a crewed Neptune mission, using propulsion technologies that actually exist or are under serious funded development, tend toward the higher end of that range. 15 years, 18, 20. These are not abstract numbers. They are human lifetimes. A crew that launches toward Neptune in their early 30s would arrive in their mid-40s to early 50s. They would have spent their entire middle adulthood inside a spacecraft, roughly the size of a modest apartment. Their muscles would have atrophied despite exercise countermeasures. Their bones would have lost density. Their cardiovascular systems would have adapted to microgravity in ways that would make readapting to any gravitational environment, including Neptune's moons, a serious medical challenge. They would have accumulated years of radiation exposure from galactic cosmic rays and solar particle events, significantly elevating their lifetime cancer risk and potentially causing measurable cognitive decline. And they would still only be at Neptune. The return trip, if one is planned, would take a comparable amount of time. A round trip to Neptune and back could consume 30 to 40 years. A crew member who left Earth at age 32 could return at age 65 or 70, having spent their entire working life, their entire middle age, their entire period of peak physical and cognitive performance inside a sealed metal container hurtling through interplanetary vacuum. Their children, if they had any, would be older than the crew member was at launch. Their parents would almost certainly be dead. Their friends, their colleagues, their communities would have moved on, changed, dissolved, reformed. The world they returned to would not be the world they left. Compare this with a crewed Mars mission, the most ambitious deep space expedition that any space agency is actively planning. A Mars mission, using conventional propulsion, involves a 6 to 9 month transit each way, with a surface stay of several months to over a year. The total mission duration is roughly 2 to 3 years. This is already considered an extreme challenge. NASA's Human Research Program has spent decades studying the physiological and psychological effects of missions on this timescale, and the list of unresolved risks remains long. Radiation exposure, bone loss, muscle atrophy, cardiovascular deconditioning, visual impairment, immune system dysfunction, circadian disruption, and a battery of psychological risks including depression, anxiety, interpersonal conflict, and cognitive decline. A 2 to 3 year Mars mission sits at the outer edge of what current medical science believes the human body and mind can endure without irreversible harm. A Neptune mission would last 5 to 15 times longer. Every risk that applies to Mars applies to Neptune, multiplied by duration. Radiation dose is cumulative. A 15-year transit exposes the crew to 5 to 7 times the radiation of a Mars transit, pushing total dose well beyond the limits that any space agency currently considers acceptable. Bone loss continues throughout microgravity exposure. Even with daily exercise, astronauts on the International Space Station lose roughly 1 to 2% of bone mineral density per month. Over a decade-plus transit, the cumulative loss could render the crew's skeletons dangerously fragile. Muscle atrophy follows a similar trajectory. Cardiovascular deconditioning, in which the heart adapts to microgravity by weakening and changing shape, has been documented in every long-duration spaceflight study. Over 12 to 20 years, the crew's bodies would adapt so thoroughly to weightlessness that returning to any gravitational environment, Earth, Triton, even partial gravity might cause serious or fatal cardiovascular events. But the clinical language of bone density and cardiovascular deconditioning conceals the lived reality of what 12 to 20 years inside a spacecraft would actually feel like. Not as a medical case study, as a life. Imagine waking up on day 1000 of the outbound transit. You have been inside this vessel for nearly 3 years. Neptune is still at minimum 9 years away. You rise from a sleeping compartment roughly the size of a phone booth. Private space is a luxury that a deep space vehicle cannot afford, and you float into the common area where you have eaten every meal for 1,000 consecutive days. The faces around you are the same faces you have seen every morning for 1,000 consecutive mornings. You know these people better than you have ever known anyone. You know how they chew. You know what expression they make when they are irritated and trying to hide it. You know which one hums under their breath during maintenance tasks, and which one goes silent when they are afraid. These are your crewmates, your colleagues, your only social world, and you will see no other human face in person for the rest of the decade. The sun, visible through whatever small viewport the spacecraft affords, is noticeably smaller than it was at launch. Not dramatically at 3 years out, you are perhaps somewhere between Jupiter and Saturn distance, and the sun is still a recognizable disk. But it is smaller, dimmer, cooler in appearance, and it will continue to shrink, month by month, year by year, for the rest of the outbound journey. There is no moment when the shrinking stops and reversal begins. There is only the slow, inexorable contraction of the brightest object in the sky, a visual metronome counting down the distance between you and everything you left behind. You exercise for 2 hours, as you do every day, because the alternative is arriving at Neptune with bones so brittle they fracture under the strain of moving in a spacesuit. You eat a meal assembled from stored provisions or grown in the onboard agricultural module, a small, brightly lit chamber of hydroponic trays where lettuce, radishes and soybeans grow under artificial light. The fresh food is a psychological lifeline. NASA research on the International Space Station has shown that growing and eating fresh vegetables provides measurable psychological benefit to isolated crews, a tangible connection to biological life in an environment otherwise defined by metal, plastic, and recycled air. But the agricultural module is also a constant source of anxiety. A fungal contamination, a lighting failure, a water pump malfunction, any disruption to the growing cycle threatens not only nutrition but morale. The crew tends the plants with the attentiveness of people who understand that these small green organisms are, in a very real sense, keeping them sane. You perform maintenance. Every day there is something. A filter to replace, a sensor to recalibrate, a seal to inspect. The spacecraft is a machine, and machines degrade. Components designed for 5-year lifespans are being asked to function for 15. Redundant systems provide backup, but redundancy has limits. When the backup fails, there is no backup to the backup. The crew maintains a meticulous log of every component's operational history, tracking performance curves, predicting failures, cannibalizing non-essential systems for spare parts when necessary. The spacecraft is slowly consuming itself, converting redundancy into continued operation, and with each year that passes, the margin for error narrows. You mark a birthday, not with celebration. Suppliers do not permit extravagance, but with a notation in the mission log and a private moment of reflection. You are now older than you were when you launched. You are aging in interplanetary space, spending what should be the most productive decades of your life between the same walls, the same faces, the same recycled air. Somewhere in the direction you came from, the people who gathered to watch your launch have returned to their lives. Some of them have had children since you left. Some of them have died. You learn about these events via delayed messages that arrive like dispatches from another century, already old by the time you receive them, impossible to respond to in the moment they describe. And you look at the mission clock and it tells you that you are not halfway there. This is not the experience of exploration as human culture has ever understood it. Magellan's circumnavigation of the Earth took roughly 3 years. Darwin sailed aboard the Beagle for 5. Lewis and Clark crossed North America and returned in just over 2 years. Even the most ambitious Mars mission concepts involve a total mission duration of 2 to 3 years, long enough to be grueling, short enough that the end is always imaginable. A Neptune transit is long enough that the middle of the journey lies years away from both departure and arrival. There is a period potentially lasting half a decade or more, during which the crew is too far from Earth to feel any connection to home, and too far from Neptune to feel any connection to their destination. They are simply in transit, in the void, moving through empty space with no landmark, no milestone, no visible evidence of progress except the slow dimming of the sun behind them and the slow brightening of a blue-black point ahead. And then there is the life support problem, which is perhaps the most intractable of all. Sustaining human life in space requires managing a closed or semi-closed loop of resources: oxygen, water, food, and waste. On the International Space Station, this loop is partially closed, water is recycled, oxygen is generated from electrolysis, carbon dioxide is scrubbed from the air, but the station still depends on regular resupply missions from Earth to provide food, replacement parts, and materials that the recycling systems cannot regenerate. These resupply missions arrive every few weeks. They carry not only consumables but also spare components for the life support hardware, which degrades and fails over time. No mechanical system operates indefinitely without maintenance. Pumps wear out, filters clog, seals crack. Electronic components degrade from radiation exposure. On the station, when something breaks, a replacement part arrives on the next cargo vehicle. A crew en route to Neptune has no resupply. Every gram of food, every spare filter, every replacement circuit board, every medical supply must be loaded onto the spacecraft before it leaves Earth orbit. For a 15-year outbound journey, this means the spacecraft must carry enough food for the entire crew for 15 years, or it must produce food on board through some form of bioregenerative life support, growing crops in the spacecraft, recycling waste into nutrients, maintaining a functioning agricultural ecosystem inside a sealed metal tube for over a decade. Both options present enormous engineering challenges. Carrying 15 years of food for even a small crew, say 4 to 6 people, would require tens of thousands of kilograms of provisions, adding mass that compounds the fuel problem. Growing food on board requires reliable lighting systems, nutrient delivery, water cycling, and crop management, all of which must function without interruption for the entire mission. A single crop failure, a single fungal contamination, a single breakdown in the nutrient cycling system could threaten the crew's survival with no possibility of resupply. Water recycling must achieve near-perfect efficiency. The International Space Station now recycles approximately 98% of its water, a milestone NASA achieved in 2023 with the addition of a new brine processor. That is remarkable for a station in low Earth orbit that still receives regular resupply. But even a 2% loss rate, compounded over 15 years with no resupply, would steadily drain reserves. For a Neptune transit, the recycling systems would need to operate at or above that efficiency, continuously, for the entire duration, and every component of those systems must remain maintainable by the crew using only the tools and spare parts they brought with them. If a critical component fails and no spare exists, the crew faces dehydration and death in a matter of days. Oxygen generation faces similar constraints. The electrolysis systems that split water into hydrogen and oxygen require electricity, which must be generated by the spacecraft's power systems for the entire mission. Solar panels become increasingly ineffective at greater distances from the Sun. At 30 AU, solar irradiance is 1/900th of what it is at Earth orbit, making solar power essentially useless for a spacecraft at Neptune. The only viable power source for a Neptune mission is nuclear either radioisotope thermoelectric generators, similar to those used on Voyager 2 and the Curiosity rover, or a compact nuclear fission reactor. Both technologies exist in some form, but scaling them to power a crewed spacecraft's life support systems, propulsion, communications, and scientific instruments for 15 or more years presents engineering challenges that have not been solved. All of these problems, food, water, oxygen, power, maintenance, are solvable in principle. Engineers can imagine systems that might work, but imagining a system and building one that operates reliably for 15 years without failure are fundamentally different propositions. The International Space Station has been continuously occupied since the year 2000, and it requires constant maintenance, regular resupply, and a permanent ground support team of thousands of engineers monitoring its systems around the clock. A Neptune-bound spacecraft would need to achieve the same level of reliability, with no resupply, no ground-based maintenance, and a crew of fewer than 10 people who must be simultaneously scientists, engineers, physicians, farmers, plumbers, electricians, and psychologists. This brings us to the problem that elevates Neptune from merely difficult to potentially impossible, the impossibility of rescue. On the International Space Station, if a catastrophic failure occurs, a depressurization event, a fire, a collision with orbital debris, the crew can evacuate. Soyuz or Crew Dragon capsules are permanently docked to the station, ready to return the crew to Earth's surface within hours. This is not an abstract contingency plan. It has been exercised. In 2021, the International Space Station maneuvered to avoid a piece of debris, and the crew sheltered in their return capsules as a precaution. The ability to come home in an emergency is built into the architecture of every crewed mission in low Earth orbit. On a Mars mission, the abort options are more limited, but they exist. During certain phases of the transit, particularly the early outbound leg, a free return trajectory could swing the spacecraft around Mars and back toward Earth using gravitational mechanics, arriving home within months to a year. Once the crew is on the Martian surface, evacuation becomes harder, but not impossible. The ascent vehicle and Earth return spacecraft are pre-positioned as part of the mission architecture. The timeline is longer, the risks are higher, but the concept of emergency return exists. At Neptune, there is no abort, there is no free return, there is no pre-positioned rescue vehicle. Once a crew commits to a Neptune trajectory and departs Earth orbit, they are committed. If a critical life support system fails in year 3 of a 15-year outbound transit, Earth cannot send a rescue vehicle. Even if such a vehicle could be launched immediately, which it could not, because none exists, it would take 12 to 20 years to reach the crew's location. The crew would have been dead for over a decade before help arrived. This is not a matter of insufficient funding or political will. It is physics. The distances and travel times involved in reaching Neptune are so large that the concept of rescue becomes meaningless. No vehicle can cross that distance fast enough to help. No supply ship can be dispatched in time to resupply a failing system. The crew is beyond the reach of any intervention that Earth could mount, regardless of resources, regardless of urgency, regardless of how desperately someone on the ground wants to help. To make this concrete, consider a specific scenario. It is year 8 of the outbound transit. The crew is approximately 2/3 of the way to Neptune. They are roughly 20 astronomical units from Earth farther than Uranus, deep in the outer solar system, with the sun shrunken to a small bright disk behind them. The main water recycling pump fails. Not the backup. The backup failed 14 months ago and was repaired using parts cannibalized from the backup carbon dioxide scrubber. The primary pump, the one that processes the crew's urine, humidity condensate, and wastewater into drinkable water. The crew has stored reserves, perhaps 30 days of emergency water supply. They begin diagnosing the pump. The problem appears to be a bearing failure in the centrifugal separator, a component that has been spinning continuously for 8 years and was rated for a 5-year operational life. They have no replacement bearing. They have materials, metal stock, a small machine shop for fabricating parts, but the bearing requires tolerances that are difficult to achieve with onboard equipment. They send a detailed technical report to Earth describing the failure, the diagnosis, and their proposed repair strategy. 4 hours later, roughly the time it takes for the message to cross the void, mission control receives the report. Engineers scramble, the pump manufacturers consulted, specifications are pulled from databases. Alternative repair strategies are debated, modelled, tested on identical hardware in a ground laboratory. 10 hours after the failure, Mission Control transmits a detailed response with 3 repair options, ranked by probability of success. 4 hours after that, 14 hours after the initial failure, the crew receives the response. But by this time, the crew has already attempted their own repair. They had no choice. 30 days of water reserve sounds like a lot, but a crew of 6 consumes water at a rate that makes every day precious. They could not afford to wait 14 hours for instructions. They improvised. They machined a replacement bearing using the best approximation they could manage. They reinstalled it. The pump is running again, but vibrating in a way that suggests the repair is imperfect. It may last 6 months. It may last 6 days. The instructions from Earth arrive and describe a superior repair technique, one that the crew would have used if they had known about it before attempting their own fix. But the fix is already installed. Removing it to implement the ground-based solution risks damaging the pump housing, which would create a worse problem. The crew must decide: live with the imperfect repair and hope it holds, or tear it out and try the better approach with the risk of making things worse. Mission Control cannot help with this decision in real time. By the time the crew's description of their current situation reaches Earth, and Earth's recommendation reaches the crew, another 8 hours will have passed. The pump may have failed again by then, or it may be running fine. The crew is operating in a decision environment where every choice must be made with incomplete information, without real-time expert consultation, and with consequences that cannot be reversed by calling for help. This is not an unlikely scenario. It is a representative example of what every equipment failure on a Neptune transit would look like. The crew is too far from Earth for real-time troubleshooting, too committed to the trajectory for turnaround, and too dependent on aging hardware for which no replacements exist. Every failure is a crisis managed in isolation. Every repair is permanent, because there are no second chances and no resupply. The margin that separates a functioning mission from a dying crew is the thickness of a bearing, the integrity of a seal, the remaining lifespan of a component that was never designed to operate for this long. Consider what this means for the human beings inside that spacecraft. They know, from the moment they leave Earth orbit, that they are beyond rescue. Not temporarily, not in certain scenarios, but permanently and in all scenarios. If the air recycling system fails, they must fix it or die. If a crew member develops a life-threatening medical condition, they must treat it or watch their crewmate die. If the spacecraft suffers structural damage from a micrometeorite impact, they must repair it or die. There is no cavalry. There is no backup. There is no "Houston, we have a problem," followed by a room full of engineers working through the night to bring them home. There is only the crew, the spacecraft, and the void. Every previous human explorer in history, no matter how remote their destination, has operated within some framework of potential rescue. Shackleton's crew was stranded in Antarctica for nearly 2 years, but Shackleton himself sailed 800 miles in an open lifeboat to reach a whaling station and organize a rescue party. The Apollo 13 crew suffered a catastrophic explosion halfway to the moon, but Mission Control in Houston improvised a solution in real time and guided them home. Even the most isolated Antarctic winter-over crews, unreachable by aircraft for months, know that when the weather clears, someone can come. The psychological scaffolding of every dangerous human endeavor includes, somewhere in its structure, the possibility that someone might come to help. At Neptune, that scaffolding does not exist. The crew cannot be rescued because they cannot be reached. They are not merely far from help, they are beyond the physical possibility of help arriving within any time frame that matters. This is a qualitatively different situation from any exploration scenario in human history. It is not a more extreme version of Antarctic isolation or submarine deployment or even a Mars mission. It is a different kind of experience altogether, one in which the concept of external rescue has been permanently removed from the crew's reality. Voyager 2 provides an instructive comparison. Even maintaining contact with a small robotic probe at Neptune distance pushed the deep space network to its engineering limits, requiring upgrades and improvisation just to receive a faint signal. Data transmission rates dropped to a fraction of what was achievable at Jupiter or Saturn, and Voyager 2 is a machine that requires only electrical power and a functional radio to communicate. It does not need life support, it does not need food, it does not generate waste or experience despair. A crewed spacecraft at Neptune would need to communicate at far higher data rates than Voyager 2 ever achieved. Voice, video, medical telemetry, high-resolution imagery, engineering data, all transmitted across 2.8 billion miles of vacuum, using a power system that must remain operational for decades. The communication infrastructure alone represents an engineering challenge with no current solution. And then there is the fuel problem that makes a return to Earth functionally implausible. Getting to Neptune requires accelerating the spacecraft to a high interplanetary velocity, cruising for years, and then decelerating to enter Neptune orbit. Each of these phases requires fuel. The deceleration phase is particularly punishing because the spacecraft must shed an enormous amount of velocity to be captured by Neptune's gravity. Without deceleration, the spacecraft would simply fly past Neptune, which is exactly what Voyager 2 did. Entering orbit requires a sustained engine burn that consumes a substantial fraction of the total fuel budget. Now add a return trip. To leave Neptune orbit and return to Earth, the spacecraft must accelerate again, this time from Neptune orbit to an Earth return trajectory, and then decelerate again upon arrival at Earth. The total delta V for a Neptune round trip is staggering. Under chemical propulsion, the fuel mass required would dwarf the payload mass by orders of magnitude. The spacecraft would essentially be a fuel tank with a tiny habitat attached. Even under more advanced propulsion concepts, nuclear thermal, nuclear electric, or theoretical fusion drives, the fuel requirements for a round trip remain formidable enough that many mission designers quietly acknowledge that a crewed Neptune mission, if it ever occurs, would most likely be one way. This is not a failure of imagination. It is the tyranny of the rocket equation applied to the most distant planet in the solar system. Every kilogram of return fuel must be accelerated from Earth to Neptune, which requires fuel to carry, which requires more fuel to carry the fuel, in an exponential spiral that makes round-trip missions to distant destinations geometrically more expensive than one-way missions. Mars is close enough that the round-trip penalty is manageable. Jupiter is far enough that it becomes extremely costly. Neptune is so far that the round-trip fuel requirements may exceed what any plausible spacecraft can carry. And this is where the title stops being metaphor. The first humans to reach Neptune would never see Earth again is not dramatic speculation. It is a straightforward assessment of the physics, the engineering, and the biology involved. The travel time alone, 12 to 20 years each way, means that a round trip would consume a significant fraction of a human lifespan. The fuel requirements for a return may be physically unachievable with any foreseeable propulsion technology. The cumulative radiation exposure over a multi-decade mission would likely exceed safe limits. The life support burden of sustaining human life for 30 to 40 years without resupply is beyond any engineering capability that currently exists or is under development. A crew that reaches Neptune would, in all probability, stay at Neptune. Not because they choose to, not because they want to, but because the distance, the fuel, the time, and the limitations of the human body conspire to make return an impossibility disguised as a theoretical option. There is a concept in orbital mechanics called the point of no return, the moment during a mission when the fuel remaining is insufficient to reverse course and return to the starting point. On a Neptune trajectory, that point arrives very early, within months of departure from Earth, perhaps sooner. Once the spacecraft has burned its acceleration fuel and committed to the interplanetary coast, the trajectory is set. The fuel remaining is allocated for course corrections and deceleration at Neptune. there is nothing left for a turnaround. The crew passes through the point of no return, almost before the mission has truly begun, and from that moment forward, they are passengers on a one-way trip into the outer solar system, propelled by momentum and governed by celestial mechanics that cannot be argued with, negotiated with, or appealed. Think about what this means for mission design. Every other crewed mission in history has included, at some level, the assumption that the crew will come home. The entire architecture of Apollo was built around return, the command module that survived re-entry, the parachutes that slowed the descent, the recovery fleet waiting in the Pacific. The Mars mission concepts under development include Earth return vehicles, pre-positioned fuel depots, and abort trajectories. The fundamental design philosophy of crewed spaceflight is bring them back alive. A Neptune mission would require abandoning that philosophy. It would require selecting crew members who understand, accept, and consent to the near certainty that they will never return to Earth. Not because the mission planners want to abandon them, but because the distance makes retrieval physically implausible. This is not a design failure. It is a consequence of where Neptune sits in the architecture of the solar system so far from Earth that the logistics of return exceed the capabilities of any technology that the current generation of engineers can realistically build. Mars is hard. Everyone who works in space exploration will tell you that. Mars is the hardest thing humanity has ever seriously contemplated attempting. But Mars is hard in a way that looks like a bigger version of problems we have already solved. Longer flight times, more radiation shielding, better life support, bigger rockets. These are engineering challenges of scale, not of kind. We know how to build rockets, we know how to recycle water, we know how to shield against radiation, we just need to do more of all of it. Neptune is hard in a different way. Neptune is hard in a way that calls into question whether crewed spaceflight, as it has been practiced and conceived for the past 60 years, can even be applied to destinations at this distance. The problems are not bigger versions of existing problems. They are new problems, problems of duration, isolation, irreversibility, and human fragility that have no precedent in the history of exploration and no solution in the current engineering toolkit. A crew at Neptune would not be explorers in the tradition of Magellan or Shackleton or Armstrong. They would be something the human species has never produced before. Voluntary exiles, committed to a destination from which return is physically implausible, sustained by systems that must operate without failure for decades, separated from Earth by a communication delay that transforms every human connection into a delayed echo. And this is where the title stops being dramatic language and starts being physics. The first humans to reach Neptune might never see Earth again, not because they chose not to return, but because the distance itself makes return a problem that may have no realistic solution. Go back to the title, understand it again. Why the first humans to reach Neptune would never see Earth again. Sit with each word. Not as a dramatic headline designed to generate clicks. Not as poetic exaggeration crafted for emotional impact. As a description of physical reality, the phrase, "never see Earth again," operates on multiple levels simultaneously, and every single one of them is true. The most literal level is optical. Earth, from Neptune's distance, is invisible to the unaided human eye. At approximately 29 astronomical units of separation, the closest Earth and Neptune ever come to each other, our planet is a faint speck of reflected sunlight, lost in the glare of a diminished sun. A crew at Neptune could aim a telescope back toward the inner solar system, and with patience and precise pointing, locate Earth as a pale pixel of blue light. But lower the telescope, look out the viewport with naked eyes. Scan the sky from horizon to horizon. Earth is not there. It has not been destroyed. It has not disappeared. It has simply fallen below the threshold of human perception, swallowed by distance into a category of objects that exist but cannot be seen, known but not experienced, real but no longer present. This visual absence matters more than it might seem. Human beings are visual creatures. We process the world overwhelmingly through sight. When we leave home to travel, we carry mental images of the places and people we left behind. but we also rely on visual anchors to maintain our sense of connection. A sailor far from shore can still see the sun that rises over their family's home. A soldier in a foreign land can still look up at the same moon. The Apollo astronauts, the farthest any human beings have ever travelled from Earth, could look out their windows and see their home planet enormous, luminous, heartbreakingly close, filling the black sky with blue and white and green. The image of Earth from the moon has become one of the most powerful photographs in human history, precisely because it captures the visual reality of home as seen from a great distance. The planet is far away, but it is right there, visible, beautiful, waiting. From Neptune, that image does not exist. The Earth that the crew left behind has shrunk beyond the resolving power of human eyes. The visual proof that home exists has been removed from their daily experience. They cannot glance out a window and feel reassured. They cannot photograph Earth with a handheld camera and send the image to their children. The planet they came from has become an abstraction, a coordinate in a navigation computer, a dot in a telescope's field of view, a set of memories that grow older and less vivid with each passing year. But the visual disappearance is only the outermost layer of a much deeper loss. The second level is communicative. As we have already seen, a crew at Neptune experiences a one-way communication delay of approximately 4 hours. Every message they send toward Earth travels for 4 hours before anyone receives it. Every reply takes 4 hours to return. A round-trip exchange consumes 8 hours. This delay does not merely slow down communication. It destroys the fundamental structure of conversation, the real-time exchange of words, the immediate response to tone and emotion, the shared present tense that allows two human beings to feel that they are together even when they are apart. A crew at Neptune cannot have a conversation with anyone on Earth. They can exchange messages. They can record video logs and send them toward the inner solar system and receive video logs in return. But the human experience of talking, of saying something and seeing the other person's face change, of asking a question and hearing the answer while the question still feels alive, of laughing together at something that is funny right now is gone. Every exchange is a monologue received hours after it was spoken, responded to with another monologue received hours after that. The emotional texture of human communication, the responsiveness that makes connection feel real, has been stripped away by the speed of light and the width of the solar system. Over months and years of this displaced correspondence, Earth would undergo a transformation in the crew's inner life. It would gradually cease to be a place that exists in the present and become a place that exists only in the past. Every piece of news from home arrives stamped with a 4-hour delay that makes it historical by the time it is received. Every image of a loved one's face shows them as they looked 4 hours ago, not as they look now. Every event that the crew learns about, a birthday, a graduation, a death, a disaster, has already happened, already been processed by the people who experienced it, already begun to fade from immediacy into memory. The crew receives Earth's present as Earth's past, and responds to it with messages that arrive as their own past. Two timelines running parallel but never touching. Two presents that cannot share a single moment. The third level is temporal in the broadest sense. A Neptune mission under any plausible propulsion technology requires 12 to 20 years of one-way transit. During that time, the crew ages, but so does everyone they left behind. Children grow up, partners age, parents grow old and die. The social fabric of the crew's life on Earth, the relationships, the communities, the shared context that makes a person who they are erodes and transforms with every passing year. After 5 years of transit, the crew's friends have moved, changed jobs, made new friends who do not know the crew. After 10 years, the crew's children have become adults who have lived more than half their lives without a parent present. After 15 years, the world the crew left behind is a different world, not metaphorically, literally, politically, culturally, technologically, socially. 15 years of human civilization produces changes so profound that a person who left in one era returns to another, except that at Neptune, they do not return. Or if they do, the return itself consumes another 12 to 20 years meaning the total separation stretches to a quarter century, or 3 decades or more. The crew member who left Earth at age 32 returns at 60 or 65 to a world that has changed beyond recognition, and that contains almost no one who remembers them as they were. Their children are middle-aged, their grandchildren are strangers. The culture has evolved, the technology has advanced, the language itself may have shifted in subtle ways that make the returning crew feel like visitors from another era. This is what never see Earth again means at its deepest level. It does not require that the crew literally cannot return. It only requires that the distance and time involved in reaching Neptune are so vast that Earth, as a lived reality, as a place where you know people, where you belong, where your presence matters in the daily flow of human life, has effectively ceased to exist for the crew long before they arrive at their destination. The Earth they left is gone. It was gone within the first few years of transit, consumed by the relentless passage of time that transforms every fixed point in a human life into something fluid, changed, unrecoverable. There is a concept that does not yet have an official name in astronautics or psychology, but that this journey requires. Call it the exile horizon. It is the distance from Earth beyond which a human crew is no longer functionally connected to their home planet in any meaningful real-time sense. Not a hard boundary, not a wall, but a gradient, a zone in which communication delay, travel time, rescue impossibility, and temporal displacement accumulate to the point where Earth stops functioning as a home base and starts functioning as a memory. Mars sits well inside the exile horizon. The communication delay is painful but manageable. The travel time is measured in months, not decades. Return is difficult but achievable. A Mars crew would miss home, would suffer from isolation, would face genuine psychological hardship, but they would also know, at every moment, that Earth is still there, still reachable, still part of their operational reality. They can go back. Jupiter pushes closer to the exile horizon. The communication delay grows to roughly 35 to 50 minutes each way. The travel time, under plausible propulsion, extends to years. Return becomes a major logistical challenge, but Earth remains part of the crew's world, delayed, distant, but connected. Saturn and Uranus push deeper into the danger zone. At Uranus, the communication delay exceeds 2.5 hours each way. Travel time reaches a decade or more. The life support burden becomes extreme. The abort options narrow to almost nothing. A crew at Uranus would feel the exile horizon closing around them, the tether to Earth stretching dangerously thin. And then comes Neptune. At Neptune, the tether snaps. The communication delay is 4 hours. The travel time is 12 to 20 years. The fuel for return may not exist. The rescue infrastructure does not exist and cannot be created. The crew's bodies have accumulated years of radiation damage and microgravity adaptation. The world they left behind has moved on without them. The people they loved have aged, changed, in some cases died. The Earth they carry in their memories no longer corresponds to the Earth that exists. This is the exile horizon, and Neptune crosses it. Now consider what the crew would actually experience upon arriving at Neptune after more than a decade of transit. They would emerge from their interplanetary cruise into the orbit of a world unlike anything human senses evolved to process. Neptune is a sphere of compressed gas and exotic ice, 49,000 kilometers in diameter, wrapped in an atmosphere of hydrogen, helium, and methane that gives it a deep blue-black color in the dim light of a sun diminished to a piercing dot against the black. The planet's upper atmosphere churns with supersonic violence, driven by an internal heat engine that scientists still cannot fully explain. Storm systems wider than continents appear and dissolve within years. Bands of methane ice clouds streak across its face, shearing apart and reforming in patterns that would dwarf any weather system Earth has ever produced. It is a world of unrelenting atmospheric fury wrapped around a core of exotic matter. Below the visible cloud tops, Neptune's interior descends into conditions that exist nowhere else in the accessible solar system. Temperatures and pressures rise with depth, until the atmosphere merges into a mantle of superheated water, ammonia, and methane, compressed into exotic states of matter superionic ice, where oxygen atoms lock into a crystalline lattice, while hydrogen ions flow freely like a liquid, creating a material that is simultaneously solid and fluid. Deeper still, pressures reach millions of atmospheres, and temperatures climb to thousands of degrees. Some models suggest that carbon atoms in Neptune's interior are squeezed into diamonds that rain downward through the mantle like hailstones, accumulating in a layer of diamond precipitation around the planet's rocky core. The core itself, roughly Earth-sized, sits at the center of this exotic inferno, crushed under a weight of gas and ice that no human instrument has ever directly measured. The crew would orbit this world, studying it with instruments that could reveal what Voyager 2's brief flyby only hinted at. They would map Neptune's magnetic field, a bizarre, tilted, off-center structure that does not align with the planet's rotational axis, and whose origin remains poorly understood. They would observe the atmosphere in detail across multiple wavelengths, tracking storms, measuring wind profiles, analyzing chemical composition. They would study the ring system's faint, dusty arcs of material that Voyager 2 confirmed, but could not fully characterize. And they would encounter Triton. Neptune's largest moon is almost certainly a refugee from the Kuiper Belt, captured by Neptune's gravity at some point in the solar system's history. The evidence for capture is written in Triton's orbit, which circles Neptune the wrong way, a gravitational impossibility for any moon that formed alongside its parent planet. Triton was born elsewhere, wandered too close, and was seized. The capture process likely involved the destruction of whatever companion Triton may have originally orbited, with a binary system disrupted by Neptune's gravitational field. One body captured, the other flung away into the outer solar system. Triton's surface is one of the youngest in the solar system, meaning it has been resurfaced repeatedly by geological activity. Voyager 2 found Triton to be startlingly active dark jets of material, erupting from beneath the frozen crust and climbing miles into the moon's vanishingly thin atmosphere, powered by processes that remain poorly understood. At a surface temperature of -235 degrees Celsius, Triton is one of the coldest known objects in the solar system, and yet it is geologically alive. Something beneath the surface is generating heat, driving activity, preventing the moon from becoming a dead, cratered ball of ice. Some scientists have proposed that Triton harbours a subsurface ocean, a layer of liquid water maintained by tidal heating from Neptune's gravity, similar in concept to the oceans suspected beneath the surfaces of Europa and Enceladus. If Triton possesses a subsurface ocean, it would be one of the most scientifically significant discoveries in the history of planetary exploration. An ocean world at the edge of the solar system, captured from the Kuiper Belt, harbouring liquid water beneath a crust of frozen nitrogen. The astrobiological implications alone would reshape our understanding of where life might exist in the cosmos. A crew orbiting Neptune would have the opportunity to study Triton in detail that no robotic mission could match, deploying instruments, conducting close flybys, potentially even landing on the surface to sample the geyser plumes and search for organic chemistry. The science would be extraordinary, revolutionary, worth careers, worth lifetimes of study, worth whatever risks and sacrifices the mission demanded. But here is the paradox that sits at the heart of all of this. The crew conducting this science-producing discoveries that could redefine humanity's understanding of the solar system and the possibility of life beyond Earth would be doing so in almost total isolation from the civilization that sent them. Their findings would take 4 hours to reach Earth. The celebration, the peer review, the public wonder, the impact of their work on human knowledge, all of it would unfold on a planet they cannot see, in a timeline they do not share, among people who have become strangers. The crew would not experience the joy of discovery the way every previous explorer has experienced it, as a shared moment, a collective triumph, a story told and received and celebrated in real time. They would experience it alone, in a spacecraft orbiting an ice giant at the edge of the solar system, surrounded by the most alien landscape any human has ever witnessed. They would make discoveries that change the world and then wait 8 hours to learn that anyone on Earth has heard. This is the deepest form of the exile that Neptune imposes, not merely physical separation, not merely communicative delay, but experiential isolation, the severing of the shared human present that makes achievement meaningful, that makes suffering bearable, that makes life feel like participation in something larger than oneself. On Earth, when something wonderful or terrible happens, you can turn to the person next to you and say, "Did you see that?" And they saw it. You share the moment. It becomes real because it was witnessed, because it was communal, because the people you care about experienced it alongside you. At Neptune, the crew's experiences are witnessed only by each other. The rest of humanity learns about them hours later, processes them in a different emotional context, and responds with words that arrive hours after that. The crew's present is never Earth's present. Their joys are never shared in real time. Their fears are never soothed in the moment they are felt. Their discoveries are never celebrated while the excitement is still fresh. Everything is displaced, delayed, disconnected, and this disconnection compounds over time. In the first months of the mission, the crew would probably maintain vigorous correspondence with Earth, sending detailed reports, receiving encouragement, exchanging personal messages with loved ones. But as the months become years, and the years become a decade, the correspondence would thin, not necessarily because anyone stops caring, but because the delay makes every exchange feel increasingly hollow. You send a message about your feelings today, and the response addresses your feelings of 8 hours ago. You ask a question about something happening on Earth, and the answer describes a situation that has already changed by the time you receive it. The emotional return on investment in communication diminishes steadily, and the crew begins to turn inward, relying more on each other and less on a planet that feels increasingly abstract. This is the process by which Earth transforms from a home into a memory. Not a sudden break, but a gradual fading, a slow erosion of presence that turns the planet you came from into something you think about rather than something you interact with. The crew would still know Earth exists. They would still care about the people on it. But Earth would occupy a different category in their consciousness, no longer a living, immediate reality, but a historical fact, a place they used to live, a world they left behind. There is a profound irony in this. Neptune is inside the solar system. It orbits the same sun. It follows the same gravitational laws. By the standards of interstellar distance, Neptune is practically next door a neighbour, separated from Earth by a mere 4 light hours, compared to the 4 light years that separate the Sun from the nearest star. In the language of astronomy, Neptune is local. It is ours. It belongs to the same family of objects that includes our own comfortable blue world. And yet, for a human crew, reaching Neptune would feel less like exploring the solar system and more like leaving it. The boundary between our solar system and beyond human reach does not align with the heliopause, the distant shell where the solar wind gives way to interstellar medium. It does not align with the gravitational sphere of the Sun's influence, which extends for roughly 2 light years in every direction. The boundary that matters for human beings, the boundary between the region where Earth can still function as a home and the region where it cannot, lies much closer. And Neptune is on the wrong side of it. This means that the first genuine exile in human history would not occur when a spacecraft crosses into interstellar space. It would occur right here, within the gravitational embrace of our own star, at a planet that appears on every classroom poster of the solar system, that children learn about in elementary school, that astronomers classify as simply the 8th planet from the Sun. Neptune is familiar in name and utterly alien in consequence. We know what it is. We do not yet understand what reaching it would mean. What it would mean is this: a crew at Neptune would be the most isolated human beings who have ever lived. More isolated than any Antarctic researcher, any submariner, any prisoner, any castaway on any island in any ocean in the history of the world. They would be isolated not merely by distance, but by time, by physics, by the fundamental structure of the universe that limits the speed of information and the reach of human logistics. They would be isolated in a way that cannot be remedied by better technology, faster rockets, or stronger radio signals. The isolation is inherent in the distance. It is woven into the fabric of the solar system itself, and they would know it. Every day, looking out at Neptune's blue-black clouds, or at Triton's geyser-scarred surface, or at the faint point of the sun hanging in an unfamiliar sky, they would know that no one is coming. No rescue ship, no resupply vehicle, no evacuation capsule, no voice arriving in real time to say, "We are here. You are not alone." They would have each other 4, 5, maybe 6 human beings sharing the most extreme experience in the history of the species, and they would have the delayed, echo-like correspondence with a planet that has become more idea than place. That is all. The terror of Neptune is not the cold. It is not the wind, it is not the darkness or the radiation or the exotic chemistry of an ice giant's interior. The terror of Neptune is what it reveals about the solar system we thought we knew that it contains, within its own borders. Distances so extreme that crossing them transforms human beings from explorers into exiles. That reaching the outermost planet does not extend the human presence into new territory, so much as it severs the human present from everything that makes presence meaningful. That the solar system, our solar system, the neighborhood we grew up in, contains within itself a frontier that functions not as a boundary to be crossed, but as a separation to be endured. The first humans to reach Neptune would stand at the edge of something. Not the edge of the solar system, the Kuiper belt extends beyond, and the Oort cloud extends beyond that, and the sun's gravitational influence reaches farther still. They would stand at the edge of human belonging, the last point where a person can still plausibly call Earth their home, still maintain some tattered connection to the species and the civilization that produced them. One step farther, and even that connection dissolves. They would look back, through whatever telescope their spacecraft carries, and find Earth, a pale blue pixel, barely distinguishable from the background stars, 4 light hours away. A planet where 7 or 8 or 9 billion people are living their lives, waking and sleeping, building and destroying, loving and grieving, utterly unaware that a handful of their species is watching from the darkness, waiting for a reply that will take half a day to arrive. Earth would still be there. It would still be real. The oceans would still be blue. The continents would still turn beneath the clouds. But for the crew, it would have crossed a threshold from a place they live to a place they remember, from a home to an origin, from a presence to an absence that fills the sky with silence. And that silence, not the cold, not the distance, not the wind, is the real terror of Neptune. Inside our own solar system, orbiting our own star, there exists a planet so far away that reaching it would mean leaving behind everything that makes human life feel human. Not the biology. The biology travels with you, not the intelligence. You bring your mind wherever you go. What you leave behind is the web of connection, immediacy, shared time, and mutual presence that allows a human being to feel that they belong to something larger than themselves. At Neptune, that web is gone, and what remains is the most profound solitude the universe has ever offered a conscious mind. The first humans to reach Neptune would never see Earth again. Not because it disappears, not because it is destroyed, but because the distance between here and there is large enough to turn a planet into a memory, a home into a concept, and a civilization into a whisper that takes 4 hours to arrive and carries the chill of a world that has already moved on without you. Neptune is not the edge of the solar system, it is the edge of us.